So, welcome guys. Welcome to another presentation. In fact, it's the first presentation for 2024. And in this presentation, I'm going to discuss more advanced exposure techniques. That means we're going to have a quick look at the old analog exposure triangle. We're going to discuss some technical information, which is important for digital photography. And then how to manage or control your image sensor, and why modern digital cameras can do more. So I want to start with some oversimplified information that's in the marketplace. So the first example that I want to quickly discuss is what I call the size and capture theory, or it's normally related to sensor size. So the theory says, if you look at the left here, large sensors capture more light and therefore they have better image quality or dynamic range. They have less image noise and a smaller depth of field the bigger the sensor is. Bigger sensors have more background blur and better bokeh. And bigger sensors give us better subject separation, or the so-called full frame look. And then you often hear that people say full frame lenses deliver more light to the sensor than the M4.3 lens. If you go to the right, then you can see why people believe this, because in almost every crop sensor review on social media, you will find statements like these. Now, I use DP Review because they are well known and probably the biggest site on social media. And here you see, interesting, although the EM5.2's shadows are noisier than the Nikon's, then it says it's proportionate to its sensor size. So immediately the sensor size, or the size and capture theory, is being used here. Olympus is receiving around 2/3 less light than the Nikon. And the Nikon in this case is an APC sensor, because the sensor is smaller on micro four thirds. And it ends this paragraph here by saying the difference between the two cameras mainly comes down to sensor size. So this establishes the social media knowledge or message that the size and capture theory is something accurate and it's something people should take note of. In the next review, we get similar statements like smaller sensor means it has more noise to deal with, while the larger sensor goes against small and large. And then the APC of the D5500 shows a significant noise advantage as expected due to its large sensor. But then they make an interesting statement here in the final sentence. They say, finally, the EM10 catches up to the larger sensor of the Sony a6000, probably because the a6000 tends to be a bit of an underperformer with respect to low light image quality. Now, this is profound. This last statement is really interesting because they're hinting to the fact that there are more than the size and capture theory only. So the size and capture theory in even the reviewer's mind is not the only variable that we should look at in terms of image quality, dynamic range, and. And that brings me to the final part here on the left. Why is this an inconsistent theory? Because older and newer cameras are not consistently the same. So you would find, if you look at a 12D, the first full-frame camera from Canon, then it's way more noisier than a 6D, for example, a more recent camera from Canon. So if the theory was consistent, then all full-frame sensors would have been equally good, or all APC sensors would have been equally good, and there would always be a difference between micro four thirds APC and full frame, because this is what what is advertised. This is what we are told. Another example is the Sony a7 II, and then the next model, the a7 III, and there are definite differences between these two cameras. So the a7 III has less noise than the a7 II, and it also has a different type of noise than the a7 II. It has more dynamic range, and the image quality is generally accepted as being better than the previous camera or the previous model. And what's interesting is they are both obviously full frame cameras, and they are both 24 megapixels. So according to the size and capture theory, these two cameras should be identical. Why is this important? It's important because if you make your purchasing choices on the size and capture theory, and you get a good second-hand a7 II, and you go and buy that camera on the promise that you will get better image quality, less noise, and you will be totally surprised once you start using the a7 II and realize that it's maybe, or in many cases, it has this a similar performance to the Micro Four Thirds, or like something like the EM1 II or the EM1 III. Now I did that. I bought the a7 II and I experienced exactly this. Another piece of information that we receive, or that is presented to digital photographers, one can probably say daily, or in so many videos on YouTube, is the exposure triangle. So people are training photographers on how to use the exposure triangle. But there's a little bit more about the exposure triangle that we need to know to understand why it's a potential problem. So the exposure triangle is more applicable to analog or film cameras than to digital cameras. And the reason is simple. On the left, you have an analog exposure triangle, and on the right, you have a digital exposure triangle. We have the shutter speed, the aperture, with the effects of these two adjustments. And on the analog camera, you have an ISO sensitivity setting. So when I buy a film roll, I can select a 100, 200, or 400. So if I place a ISO 400 film roll into the analog camera, you usually set the mechanical ISO setting to ISO 400, which calibrates the camera's exposure formula to the film roll, to the sensitivity of the film roll, and then you get accurate exposures on your images. On the digital exposure triangle, you still have aperture, shutter speed with the effects, but the ISO is now an image brightness adjustment. More correctly, it's an amplifier. So it takes the image signal coming off the sensor and it amplifies it. So if you take a auto exposure image, say in aperture mode, then the camera will select the shutter speed for the aperture that you selected, and it will adjust the ISO. And at the end, you will get an 18% gray image, which is a correctly exposed image. And in a darker area, the camera will increase the ISO. In other words, the image brightness from the image signal coming off the sensor. So it's a brightness adjustment, and it's used ongoing. It changes always on a digital camera, where on an analog camera, it stays the same for the film speed that you're using. And there are more confusing technical statements which we should take note of. The one is that the ISO setting adjusts sensor sensitivity, which is not accurate. The sensitivity of your sensor has been set in the factory. So it's a once-off adjustment to the sensor, and it never changed thereafter. The ISO image brightness amplifier changes the brightness of the image signal coming off the sensor. And then you hear people say, yeah, but your Olympus camera has inaccurate ISO settings. I don't want to spend too much time on this. This is again a confusing statement which is irrelevant. And please read my articles for more about that. Or they will say the camera's histogram is inaccurate. It reads, for example, the JPEG file and display that information on the display, which is completely inaccurate. When you take the image and you prepare your camera for taking the image, there's no JPEG file. So there's nothing at that point in time. It's only after you took the image that there's a JPEG file. And a quick explanation is the histogram shows the three variables in the exposure triangle: shutter speed, aperture, and image brightness, or the ISO. If I go and fix the ISO, it displays aperture and shutter speed. If I fix shutter speed, it only displays the aperture. And you can go and test this. You can fix the aperture and the ISO and see what the shutter speed does to the histogram. Another one is crop sensors. Crop sensor or micro four thirds sensors receive less light. I disagree with that, and I'll show you. Or micro four third cameras suffer from diffraction. And this is, again, a confusing statement, and I like you to ignore these kinds of statements, especially the diffraction statement. You know, I see forum posts where people say, Olympus people say, I never go above f4.5 or f5.6. That's really, really not necessary to be that cautious in using your camera. If you're unsure, try higher aperture values. Go to f11 or go to f13. And when you're home, study the image in Photoshop and see if you are happy with the image quality and the image sharpness. If you're okay with that, keep on being creative and use it to your advantage. But don't get afraid by what other people say. So, we covered a few oversimplified statements or pieces of information, and I like to give you more technical information which will help you to do more advanced exposure control on your digital camera in the future. So the key point here is digital photography is different from analog photography, and therefore we need some more technical information. The first example is image sensors does improve, and this is important. So if you take the original EM1 and you compare it with the EM1.3 or now the OM1, then you can clearly see that the image quality coming off the sensor improved. It's in most cases less noisier than the previous models. So image sensors do evolve, they do get better, and the reason is simple. The criteria on which scientists are developing new sensors, they're looking at sensor to sensitivity, which is the quantum plus optical efficiency of the sensor, and they develop both these areas: the quantum, which is the materials and the design of the sensor, and optical, which is the capturing of the image signal and having it onto the pixel sensitive area so that we can convert that to electrons. So there's constant development and improvement in this area taking place. Second part that gets better is image processors. They have more processing power and speed, and they are faster and more advanced firmware, which is now available in the image processors. And this is interesting because we can now use different technologies or new technologies to control the noise in the camera, for example. So one of the reasons why we have a so-called noise floor on the image or in the image sensor is the control wiring every pixel has. So every pixel has a set of control wiring that's controlling the pixel. The moment you have electronic components and control wiring and a current flowing through that, you have losses, and which is translated in digital photography as noise. So when you increase the pixels, then you increase the control wiring, and then you can expect to see more noise from that camera. So how do we control the noise coming off the control wiring? they do something really interesting here. At the bottom, you can see they replace some of the control functions in the control wiring with firmware. So because we have more powerful image processors, we can now replace some of the control wiring and therefore reduce the electronic component part of the pixel and therefore having a smaller noise floor. There are also more advanced manufacturing techniques for sensors and different materials, so the quantum efficiency part of the sensor, which is improving. So here you can clearly, from this short discussion, you can see why image sensors do improve. The second point is something really interesting. It takes us back to the size and capture theory, which basically says the smaller one is not as good as the big one. Okay, this is what this line. So if you look at the horizontal axis here, you have less and more, so depth of field and image noise. Image noise you have less on medium voltage according to the theory, and you will have more noise on the smaller sensors here. And this is what we saw in those two examples with the review, the camera reviews. On the vertical axis, you see less and more here. So dynamic range, for example, you should expect more dynamic range in a medium format and a very small dynamic range for mobile phone cameras. Background blur the same. You will have difficulty on creating background blur here, where it should be very easy up there. Is this a consistent theory? No, it's not a consistent theory, because even in one field like full frame, we see that there are dynamic range differences between 224 megapixel cameras, or there are image quality or noise differences. So should we extend this, make it a little bigger here to fit all the differences into the full frame bracket here? No, I disagree. I think it's just we can conclude that the theory is not consistent. We see it with Micro Four Thirds also. So if you look at an old 12 megapixel EP3 and you compare it to the OM1, then you would notice that the EP3 has way more noise than the OM1, but the sensor size is still the same. So what's happening here? And the reason is simple. We need to break the sensor down into two distinct areas. And the one is the technical characteristics of the sensor, which is linked to the design of the sensor and not the size. So that if I have more pixels or less pixels, if I have a more modern sensor or an old sensor, so the technical characteristics of the sensor is linked to its design, whereas the optical characteristics of your sensor fits this theory or supports this theory. So background blur, bokeh, the size of the lenses or depth of view. So you can nearly plot this graph for the optical differences between sensor sizes. And this is important. So don't let somebody confuse you and say, yeah, the image quality is absolutely better in the bigger sensor. It's not always true. Or the image noise is less in the bigger sense. It's not always true. So one really needs to drill down to pixel level and not only look at the physical size of the sensor. So there are basically three types of CMOS sensors today. The standard CMOS sensor, which is the oldest technology. So even the old 300D from Canon had a CMOS sensor. Then you have LiveMOS, which Micro Four Thirds cameras have. Which is a unique configuration. And then you have BSI sensors. And one point that's really important, it's only BSI sensors, the design of the sensor, that allows for a stacked configuration. What does a stacked configuration give us? Simply speed. So you get very quick, very fast sensors like the Sony A1 or the OM1 camera is the same. These are very, very fast readout speed cameras. So what is the difference here between these three? If you look at the old standard type sensor, CMOS sensor, then the control wiring here, you can see this is the pixel on the top here. So you have a standard CMOS on the left and a BSI on the right. The image signal is coming from the top, going through the micro lens here through the RGB filter, and in standard CMOS sensors, the control wiring is placed on top of this photon sensitive area, and it's creating obstacles and all sorts of problems for the image signal, and there's a lot of read noise happening in this area here. On a BSI sensor, the control wiring was moved to the bottom, and you have a clean image signal path, in other words, higher optical efficiency. Plus quantum efficiency, because I now get the full sensitive area to capture photons. So it's a very distinct difference here. So again, if you look at the standard CMOS sensor, here you see the control wiring. What is important to notice here is that the effective pixel area is smaller. So this is the pixel area here, and as a result of the control wiring, which is placed on top of the sensitive area, I'm reducing the effective area here. On a BSI sensor, where the control wiring is at the bottom, I have the full effective, or the full sensitive area here to work with. Micro Four Thirds cameras combine every 4 pixels combine or use the same control wiring. Therefore, I only have 25% control wiring per pixel, which also increases my effective pixel area here, or the sensitive area here. So here you can see on the left, standard CMOS has a sensitive or effective sensitive area of 65 to 72%. The LiveMOS 75 up, and BSI sensors up to 100%. Now this is interesting because you can be comparing a Micro Four Thirds to a APC sensor, and if you look at the smaller effective area of the APC sensor, which is a bigger sensor, then the Micro Four Thirds sensor might still have the edge in terms of efficiency and a larger effective pixel area. So you cannot just say the one sensor is bigger or smaller than the other. You need to look down to pixel level and really how efficient those pixels are. So pixel area also changes or impacts the sensitivity as well as the noise floor. Okay, and then another one that I want to quickly have a look at, and that is a so-called the one receives more or less light than the other one. So the subject here is transmitted via the lens onto the sensor, and the sensor, this image here needs to cover the full sensor. So we call this the image circle covering the image sensor. And on the Micro Four Thirds, it's a much smaller image circle. Now, I guess this is what the size and capture people do. They look at the difference in the image circle, and they say, okay, this lens delivered more light than the Micro Four lens. But the secret is both are delivering the full image, the full reflected image onto the sensor. So is it really less light, or is it just a more concentrated light on the Micro Four Thirds camera? So if we go to the left here, reflected light passes through the lens. We know that. The lens is designed for the image circle. That is why the full frame lens is bigger than the Micro Four Thirds lens. Pixels capture photons and not the size or the backplate, the size of the backplate of the sensor. The photons are the pixels are capturing photons. It's so important. Your pixel area changes sensor sensitivity. So larger picture areas are more sensitive and can capture more image details, especially in the shadows. That's why pixel area can make a difference. The so-called size effect of different sensors is typically here in this area here. More pixels add noise to the noise floor, as I explained before. And here are 2 interesting examples. So if I look at a full frame camera, a 6D with 20 megapixel and a pen F with 20 megapixel, then you would see that the 6D, the pixel area is almost 250% larger than the pen F. That makes a huge difference in sensitivity, in sensor sensitivity. So one would expect the 6D to capture more image detail, especially in the shadows. In the normally exposed midtones and highlights, it should be the same, but the benefit should be really in the shadows. Nothing about noise, because noise is a different technical aspect of the sensor. But if you look at a A7R5, which is 61 megapixels versus the Pen F, then you notice that the pixel area is now only 26% larger than the Pen F. And immediately that sensitivity benefit of the 6D is not present in the A7R4. So again, we see that there are technical differences between these sensors, which is really important to understand, for one, when you purchase a camera, and even when you start working with a camera. So I wouldn't expect the lowest noise level from the A7R5, simply because I have 40 million pixel control wiring, more than my Pen F or the EM13, for example. In addition, I'm sharing 4 pixels with one control wiring. Yeah, I literally have 60 million sets of control wiring controlling the sensor in this camera. Okay, so I want to move towards the final slide in terms of technical information. And this is the photons conversion to electrons graph. This is probably the most important. This is way more important than an exposure triangle. I really like to recommend digital photographers to get to know this graph, to familiarize yourself with this graph. We talked, before I do that, let me just, on the horizontal, we see the photons, the vertical electrons. So if I have this much photons hitting the sensitive area in the pixel, then I will convert to so many electrons. This electrons, it becomes the image signal, which is then coming off the sensor towards the image processor. So every sensor, and this is important, every sensor has a noise floor. The moment you have electronic components, control wiring, there's losses and there's a noise floor. We can manufacturers control the size of the noise floor by things like the micro four thirds or the LiveMore sensor format, or manufacturing techniques or different materials are used in the sensor. And then you have a short noise part, and the combined noise is my noise level of the sensor. So before I see an image signal, I need to have more photons hitting the pixel than the noise component actively in the sensor. And this is this A point, this one here, or the absolute sensitivity threshold that we call it. And from here onwards, as I add more photons, I will start seeing an image signal coming off the sensor up to the full saturation point of that sensor. This linear area here is the operating range of my sensor, and it's also called the dynamic range is defined. So if I can have a lower noise floor, I can increase my dynamic range. If I can design the sensor to have a higher saturation point, I can increase my dynamic range. See? So this is how the manufacturer would, for example, why there are differences from the one sensor to the next. Here is what we call the maximum SNR and the maximum noise level of this sensor. So we talked about SNR. If I improve, if I have more exposure, if I add more exposure to the sensor, in other words, I have more photons, then I have a higher saturation point on the sensor. What is the advantage? If I increase my saturation, I increase my SNR, the signal to noise ratio. So the clean signal versus the noise part in the signal. In this case, I will have less visible noise. If I have a lower exposure or less photons hitting the pixel, then I will have a smaller clean signal versus noise, and I will see more visible noise in my image. So this could be a midtone or a normally exposed area, and this could be shadows. So the same sensor could have different S&R values depending on well-exposed areas and shadows. And this explains why you see more noise in the shadows. Now, the size and capture theory cannot explain this because the sensor does not get smaller in the shadows. It stays the same size. But understanding this simple graph, you can start explaining, and you start understanding why things are happening in your image. And I will also show you how to cope or how to manage the sensor to have less of a noise effect. These descriptions on the right is important. Please study this. With myself, when you start with this sort of knowledge, it takes a while to get used to it. But I've been working with this now for about 3 years, and it's now so quick. So when I go, if I do photography and I see a scene, I evaluate the light quality, I evaluate the light situation of the scene, and I make very quick decisions. Should I use ETTR, yes or no? What is the shadows like? What is the diffusion like in the scene? Blah, blah, blah. It goes very quick, these sort of decisions that goes through your mind. Okay, so I just want to stress again here that we're looking at sensitivity, which is quantum plus optical. All image sensors have noise. The noise floor in the camera, you can say, is read noise, the sensor noise floor, and short noise. S&R is best at full sensor saturation. So when I fully saturate my sensor, I get the best S&R values. And then each sensor has unique technical characteristics. I think you start understanding this now. You cannot just say, the bigger one or the smaller one in terms of technical characteristics. And then the sensor size determines optical differences. So the sensor size only works in terms of optical differences. So now we can discuss the exposure formula in the camera, or we can start talking about more advanced exposure techniques, because now we understand what's happening in the sensor. So what I want you to see from this slide here is there's your typical exposure formula, and there are there are 1, 2, 3, 4, 5 variables. The sport meter calibration is a constant, so it doesn't change, but there are 4 variables changing, not only 3, like in the exposure triangle. The 4th one is the scene luminance. And I mentioned this in the previous slide. So if you look at the shadow areas and the bright areas or the midtone areas of your scene, then the luminance is different coming off the reflected areas in that scene. And this affects the saturation level of the image sensor. So in a shadow area, you will have a lower saturation level of the sensor, those pixels in that area. And in a well-lit area, you will have a higher saturation level and S&R, those pixels in that area. So you need to look at the pixels, not only the sensor. So we have 4 variables: shutter speed, aperture, ISO, as well as illumination or luminance coming onto the sensor. And we can influence that by moving our subject or using an LED panel or a flash. And now you can see why it is important, even in digital photography, to keep a flash with you. It's really confusing to tell people, no, you don't need a flash, only use higher ISOs, for example. Why is a higher ISO problematic? Because if I underexpose my sensor here, then I will get a lower S&R. You see that? If the ISO is an image signal amplifier or image brightness, then I take a low S&R value here and I just amplify it. I make the image sharper, but I still have a low S&R. That means more visible noise. The sensor didn't create, or the ISO function didn't create noise. I'm just amplifying an image signal with a low S&R. So what is our goal? To always try and have as good as possible SNR or saturation levels inside the sensor. And I'll show you how we do that. Before I do that, I'm not going to spend much time on this slide here. I did an article. Please try and go and read the article and understand how DxOMark test image quality and what they mean by good image quality and acceptable image quality. It changes also the way we interpret this ISO reading or value that they give for cameras. Go and read the article. It really helps a lot to better understand what DxO does. And in fact, DxO do not support the size and capture theory. They use the same theory that I'm using, especially in this presentation also. In other words, the technical characteristics of your sensor is different. And once you understand that, then this test data of DxOMark becomes really, really interesting and helpful. Okay, so we now reach the point where we can start discussing the digital camera in a little bit more detail. Again, this illustration here is something that I recommend you study, and you always keep it with you because this will enable you to improve your image quality in digital photography. So we're looking at 3 steps here of the image signal pass. Step 1, that's from the scene, reflected light or luminance going through this lens via the aperture shutter, exposing the sensor. The second step is the image signal from the sensor going into the TruePic image processor where you will find the ISO or the image brightness setting. And the final step is the gamma conversion from the linear data coming off the sensor. I'm putting a gamma profile onto that, and I then create my JPEG file. So the scene to the sensor to the conversion to the JPEG file. In between, we have the exposure controller. So the exposure controller is looking at all 4 values. It's looking at the aperture shutter, the ISO, as well as the luminance reaching the sensor. Okay, so it also gives information onto workspace, and that makes workspace extremely unique. So in workspace, I have the enhanced raw format, which consists of the camera settings coming off the image processor, my exposure information coming off the exposure controller, and all included in the enhanced raw format going that you now can convert your raw file or the enhanced raw file in workspace. So let's make a few quick examples here. We know that the aperture shutter exposes the sensor. That means we're looking at this graph here. So if I expose my sensor correctly, without clipping, in other words, not going above this full saturation point here, or when you look at the histogram, if you don't go too far to the right, then the sensor is fully exposed, but not clipped. So I didn't reach the top dynamic range of the sensor. But I can still clip the bright areas by selecting too high image brightness here. Why? Because the ISO is part of my exposure formula. So that the image information that will be converted could show clipped highlights here, which is in effect an ISO mistake and not an image sensor clipping. This is important because you start understanding the difference between the ineffective exposure triangle and really understanding what's happening in the camera. So now, for example, if you're in a night scene or street photography at night and you don't want the lights to clip, expose the sensor correctly, bring down the ISO, and correct the image brightness in workspace until the point that you don't see clipping on the light. So you can start using your camera completely differently to what you used to, because you didn't know, nobody showed you this picture. Everybody just wanted to let you believe that the bigger sensor is better than the smaller sensor. There's another interesting aspect that Olympus gives us, and if you again look at this here, so I'm capturing the image signal coming off the sensor going through the ISO, and the gamma conversion here. Olympus made it possible for us to tweak the gamma curve, and we do that with the tonal adjustments in the camera. So the shadows, brightness, and mid-tone adjustments in newer models, or the gradation function, or the tonal curve in Workspace. So if you want to see how I arrange my workspace the editing palette, so I use this format here to arrange my editing palette, and it looks like this. So I have my basic, you can do it in this area here with this button there. So my basic image or raw adjustments is the exposure, like I explained, white balance, picture mode, and color space. Then you have your tonal adjustments that I can tweak the gamma curve, highlights, gradation, tone curve. I have targeted color adjustments or global color adjustments, typical image adjustments, my noise filter. And just a quick note here, the noise filter in with Olympus is exceptional. It's really good. So the normal noise filter in the camera or in Workspace is in most cases enough. I use the low option for almost all my cameras. And then we have an AI option, and here you can see for the AI option only works from ISO 800 and higher. So if you're in a situation and you like to use the AI filter in Workspace, then select ISO 800 on your camera, or those cameras that can use the AI filter. And it's a brilliant AI filter. You don't need. I have Photolab 6. I never upgraded to 7 because this AI filter here is more than enough for me. I want to do a few quick examples. Here is an example of a low SNR value. So the pixels in this area of the sensor has a lower SNR. Even if I brighten the shadows, I will see noise, and I will not see the noise here because the pixels in this area was fully saturated or at a higher SNR level. Again, this explains why we see shadow noise. I want to go to the next one. Here you see good quality of light. It was late afternoon. The reflected light was not too harsh, and I didn't have to do much. It was quite easy to take the image. In fact, I took it with an old XZ2 from Olympus, and interestingly, it uses a BSI sensor. Now you would understand why Olympus selected the BSI sensor. The previous one, the XZ1, has a CCD sensor, and CCD has the same effective pixel area benefit than a BSI sensor. So having less pixels on the XZ1, you in fact have a higher sensitivity, and it should benefit shadow details a little more than on the XZ2. The next one is again a good image quality. So the quality of light was good here. And I'm focusing on the main areas. This is the main thing for this image. So the sky, the clouds, and the front area. My focus was not the trees in the background here. So I was happy with the histogram. I didn't have to do anything. I just took the image. Then here's an interesting example. Again, I have a subject in the shadows here, but not as extreme. So the SNR is okay. And then I applied a small ETTR, so I moved my histogram to the right. And this enabled me to edit without having a flash, and only edit the image to quite a good result here. And the way I did it, I used my tonal adjustments in Workspace to create a very flat curve or a flat profile in Workspace. I then transferred that in a 16-bit TIFF to Photoshop. I used the raw converter in Photoshop and did the final editing in Photoshop. And to me, the end result is quite good. Then the final example that I want to show you is the main message is to focus on the subject and not on everything in the image. So in this case, my subject is the dog and not the background here. So I didn't bother much with the SNR or the saturation level in this area because it's only fill-in information. It's not the main information of my image. The little dog is the subject here. So even though we're talking about managing the sensor, ETTR or SNR or saturating the sensor, it really depends on the scene, the quality of light, diffusing light. Is there sharp reflecting areas? How will I manage that? Make a few quick decisions and then take the image. Okay, guys, this is the full presentation. I hope it's of value to you. Please ask questions. You can also contact me via my blog. There's an email box there, and I'm quite excited to help anybody asking questions. Thank you.